Elements. All things known are made from them. Oxygen and hydrogen are found in air and water, and carbon and phosphorus in plants. Human beings are made of elements as well, like calcium, which builds our bones, and iron contained in our blood. When and where did these elements come from? And how were they formed? The Earth and the Sun were created from the essence of the universe, a result of the gathering of stardust. The elements, too, have their origin in the universe. Scientists have observed the universe, and scenarios of its birth and evolution have been written. Particle accelerators have even been constructed to study the reactions of atomic nuclei, the core matter of elements. Recently, the combination of observations, scientific theories, and nuclear physics experiments has led to a better understanding of elements. Today, it is even possible to synthesize and disassemble them in accelerators. Humankind is near the moment of solving the multitude of puzzles shrouding the birth and evolution of the elements. Humans first realized the existence of nuclei about 100 years ago. Henri Becquerel, who was studying fluorescent matter, found that something capable of exposing photographic plates radiated from ores that contained uranium. Marie Curie noted the discovery, went a step further, and succeeded in extracting an unknown substance that emitted intense rays. She named it radium. Studies on the nature of rays emitted from uranium and radium showed that there were actually 3 distinct types of rays, and that they could be separated when passed through a magnetic field. The rays were named alpha, beta, and gamma. Later on, it was learned that they were actually helium nuclei, electrons, and high-energy photons. So why are helium nuclei and electrons emitted from uranium and radium? Rutherford answered this question. The rays are emitted because the uranium and radium are in states that are unstable. Such states will, in time, allow the nuclei to emit helium nuclei or electrons, thus transforming their uranium and radium into different nuclei. Atomic nuclei are a combination of protons and neutrons. Protons, which carry a positive electric charge, and neutrons, which have no charge, are mutually attracted. They can couple together if they come near each other. This coupling mechanism, known as strong interaction, was clarified by Hideki Yukawa. Let's form an atomic nucleus by increasing the number of protons and neutrons one by one. The number of protons is indicated on the left axis, and that of neutrons on the right. The element name of each atomic nucleus is determined by the number of protons it has. The number of atomic nuclei existing in the universe is limited. The array of all such nuclei is called the chart of the nuclides. Theoretically, the predicted number of nuclides is approximately 7,000, and the number experimentally confirmed thus far is 2,000. Among those confirmed, there are 256 stable nuclei, those that do not decay. These nuclei are located near the center of the chart of the nuclides, and the number of protons and neutrons is comparable. Nuclei other than these 256 are unstable and decay according to their own lifetimes. So, how do they decay? If there are more neutrons than protons, as is in the case of oxygen-20, one of the neutrons emits an electron and an antineutrino, changes to a proton, and forms fluorine-20. This is called electron beta decay. Fluorine-20 is also unstable. Therefore, beta decay again occurs, causing a change to neon-20. The neon-20 nucleus is stable, so no further decay occurs. On the other hand, if there are more protons than neutrons, as is in the case of magnesium-20, one of the protons emits a positron and a neutrino and changes to a neutron. Magnesium-20 then becomes sodium-20. This process is called positron beta decay. Sodium-20 is unstable and again undergoes positron beta decay, changing to stable neon-20. If the number of both protons and neutrons is too large, electrostatic repulsion between protons becomes too strong and the nucleus breaks up into smaller nuclei. The product of decay is also often an unstable nucleus, so decay continues until a stable nucleus is finally achieved. An atomic nucleus is given its element name according to the number of protons in the nucleus. And within each element, there may be different nuclides, each having a different number of neutrons. These are called isotopes. For example, all carbon isotopes have 6 protons, but there can be 13 different isotopes, and the number of neutrons ranges from 3 to 16. Each isotope also has a mass number, the total number of protons and neutrons, and is named according to both its element name and mass number. For example, carbon-12. If we examine the relative abundances of atomic nuclei currently in our solar system, we will see huge variations. There is a particularly large abundance of nuclei with protons or neutrons numbering 2, 8, 20, 28, 50, 82, and 126. These values indicate especially stable atomic nuclei and are called magic numbers. Why does our sun continue to shine? What is the energy source of stars? These questions drove humankind to ponder the mystery of the creation of the elements. The sun is comprised mostly of hydrogen nuclei, protons, and helium nuclei. A helium nucleus contains 2 protons and 2 neutrons. Let's consider the possibility that 4 protons can fuse to form a helium nucleus. Perhaps this can also help us to understand how energy is generated in the sun. The total mass of 4 protons is slightly greater than the mass of a helium nucleus. Does this difference in mass generate energy? The theory of relativity states energy E equals mc squared. This means that a small difference in mass can generate a large amount of energy. But protons, which are positively charged, electrically repel each other. Under such circumstances, can nuclear fusion occur? Von Weizsäcker and Bethe and Critchfield succeeded in answering this question. The core of a star with a mass nearly equal to that of our sun has a density more than 100 times that of ordinary water and a temperature of more than 15 million degrees Celsius. The thermal motion of the protons in a star allows them to interact with each other. In rare instances, they will undergo quantum mechanical tunneling through the barrier created by their electric repulsion and can then fuse. In this reaction, one of the 2 protons emits a positron and a neutrino, and the resulting nucleus is deuterium. The positron then annihilates with an electron to produce gamma rays. The deuterium formed captures a proton, emits a gamma ray, and becomes helium-3. The helium-3 particles collide with one another, give off 2 protons, and combine to become helium-4. It is this generation of gamma rays that causes stars like our sun to shine. The gamma rays produced by nuclear fusion are redistributed in energy, becoming the visible light at the sun's surface. Since the formation of deuterium occurs rarely, helium is also formed at a slow rate. Our sun has been burning for more than 4.6 billion years. Over this long span of time, the birth and evolution of life on Earth has taken place, and our sun will continue to burn for another 5 billion years. Helium nuclei are synthesized from the fusion of protons in a star. From this, still heavier nuclei could be synthesized from the fusion of light nuclei. But where did the protons, the most basic material, come from? Did they first appear with the creation of the universe? In 1948, Gamow proposed that the universe expanded from a point of a massive explosion, what is now called the Big Bang. Contemporary science provides us a scenario of the Big Bang creation of the universe. So how were protons and neutrons born under such conditions?
The scenario of the creation of the universe, as understood at present, states that it was once very tiny, even smaller than the minute protons and neutrons we know. It is thought to have been created by the effects explained by quantum theory, from a null condition where there is no time, no space, no matter. This minuscule universe began to grow rapidly due to what is called inflation, a period of extraordinarily rapid growth. Once this began, the universe grew continuously larger, reaching a macro scale of billions of light years. Of course, this inflation and rapid growth could not last forever. And when it came to an end, our universe was an extremely hot, massive fireball, where the most elementary particles in nature, including quarks, electrons, and light, existed. Following the inflationary period, as the temperature receded, when the universe was about 1/1,000,000th of a second old, the quarks combined to form protons and neutrons. Further, when the universe was about 3 minutes old, the protons and neutrons united to form deuterium.
The deuterium nuclei collided with each other and changed to form tritium and protons. Further, each tritium nucleus could interact with the deuterium particle to form helium-4 and a neutron. During this process, free neutrons, having a short lifetime, successively transform to protons as the result of electron beta decay. Within several minutes after the Big Bang, the ratio of proton to helium abundance was 12:1. This ratio determined the subsequent evolution of the elements.
Should the masses of the proton and neutron have been more nearly equal than they are, the neutron lifetime would have been extremely long, and if this had been the case, nearly everything would have become helium. All hydrogen would have been consumed. That means no new stars could have been born and no new elements formed. Needless to say, the universe would have been lifeless.
The miraculous lifetime of neutrons led to the formation of a variety of elements and the existence of humankind. Concurrent with helium-4 formation, elements having larger atomic mass, such as lithium-6, lithium-7, and beryllium-7 formed. However, there are no atomic nuclei with a mass of 8. Even beryllium-8, formed by the mutual collision of helium-4, breaks up nearly instantaneously. Following the Big Bang, the natural world evolved towards a realm of low energy. In this case, 2 nuclei of helium-4 are more energetically favorable and are therefore more stable than existing as beryllium-8. There are no stable atomic nuclei with a mass of 8 in existence. For this reason, the synthesis of elements during the genesis of the universe reached a mass of 7 at most. So where and how did the synthesis of heavier elements start? Our fiery universe cooled down as it expanded. After about 300,000 years, the thermal energy of the electrons dropped, allowing them to be captured by the protons and helium nuclei, resulting in the formation of hydrogen and helium atoms. At this time, light previously scattered by free electrons could pass through space freely, giving visual dimension to the universe. Before long, stars began to be born. Hydrogen and helium atoms gathered in areas of high density, forming molecular clouds. Due to its own gravitational force, each molecular cloud contracted, and as it contracted, the temperature and density at the center rose. Each electron was once again separated from the hydrogen or helium nucleus to which it was bound. The rise in the thermal energy of the protons caused them to interact and form helium nuclei, and the resulting energy generation caused the star to shine. Our sun was born in this manner as well. The synthesis of helium from hydrogen nuclei proceeds inside a star. A star with a mass nearly equal to that of our sun contains sufficient hydrogen at its core to burn for approximately 10 billion years. When the hydrogen fuel in the core is exhausted and energy generation stops, with nothing to support the core, the star undergoes gravitational contraction. The temperature and density at the core rise further, whereupon something unexpected occurs. The mutual collision of helium nuclei can then happen frequently. 3 helium nuclei collide nearly simultaneously and form carbon-12. Carbon-12 is a stable nucleus and can fuse with another helium to form oxygen-16. This leads to the creation of elements surpassing the atomic mass of 8. A star with a mass nearly equal that of our sun ultimately dies with the formation of a carbon-oxygen core. Stars with much larger masses will evolve beyond this stage. In massive stars, the synthesis from hydrogen nuclei to helium nuclei proceeds by a reaction called the CNO cycle. In the CNO cycle, the carbon, nitrogen, and oxygen contained in the star since its birth react successively with protons. 4 protons are consumed, and 2 positrons and 2 neutrinos are emitted in a single cycle to form a single helium-4 nucleus. This produces the energy that powers massive stars during their CNO cycle burning phase. The hydrogen fuel at the core is depleted in approximately 10 million years. The helium ash produced in the CNO cycle is then converted to carbon and oxygen. At this time, the higher core temperature reached in massive stars results in the formation of neon from carbon fuel, and the formation of magnesium and oxygen follows from neon fuel. Inside that core, a silicon and sulfur core is formed from oxygen fuel. Then, at the very center of the star, iron and nickel are formed from the silicon and sulfur. In stars with masses more than 10 times that of the Sun, the different atomic nuclei are layered through these processes, forming an onion-like structure. It is in this way that the compositions of elements up to iron and nickel emerge. Iron and nickel are the most stable atomic nuclei. In other words, they have the smallest energies or masses per nucleon. If we plot mass per nucleon along a third axis perpendicular to the chart of the nuclides, a valley is formed with the region of stable nuclei running along the center. This valley is deepest around the iron and nickel isotopes and is referred to as the Valley of Beta Stability. Stellar nucleosynthesis progresses downward along the Valley of Beta Stability from the lighter nuclei towards iron and nickel, located in the bottom of the valley. From this point, the slope changes from downward to upward. Yet no fusion reactions occur to form the heavier elements found along the uphill slope. So there must be different processes to form new atomic nuclei following the creation of iron and nickel. Copper and zinc, indispensable for life as we know it, have not yet been formed. As for elements that play important roles in our daily lives, silver lies beyond the iron and nickel formation process. And gold and even uranium far beyond. So what are these new processes, and how are they different from fusion reactions? Free neutrons are unstable. However, if there is a continuous neutron source, the freshly generated neutrons can be used as a crucial material in the creation of elements heavier than iron. Stars called red giants hold this neutron source. Stars with masses of 8 or more times larger than the Sun explode at the end of their lives, scattering the elements they have synthesized, such as carbon and iron, into space. Interstellar gases gradually increase their abundances of elements, such as carbon and iron, and coalesce, and then give birth to a new generation of stars. Of the new stars, those with masses about 1 to 8 times that of the Sun will evolve into red giants. Inside the red giants, some of the CNO cycle reactions can operate. By virtue of convection, carbon-12 captures a proton to form nitrogen-13, and then carbon-13 is formed via beta decay. Carbon-13 interacts with helium, forming oxygen-16 and a neutron. This series of reactions is the neutron source. Since no Coulomb barrier exists, the neutrons are easily captured by the atomic nuclei. To begin with, iron-56 captures a neutron to become iron-57. Iron-57, which is stable, captures another neutron as well, creating iron-58. Iron-58 is also stable and captures a neutron to become iron-59. Iron-59 is unstable and evolves to cobalt-59 when one of its neutrons changes into a proton as the result of electron beta decay. This is one way that elements heavier than iron are synthesized. Since the source produces a low neutron density, transformation is gradual, taking thousands of years to progress to heavier elements. This is the slow neutron capture process, or the S process. The primary feature is that the neutron captures proceed slowly compared to typical beta decay lifetimes. Elements continue to capture neutrons as they evolve, finally reaching bismuth-209.
Bismuth-209 is a very heavy atomic nucleus, Up to this point of the nuclear chart, many stable nuclei heavier than iron were formed by the S process. However, elements with masses heavier than 209, such as uranium and thorium, which are unstable but long-lived, cannot be created by this process.
Bismuth-209 transforms to bismuth-210 through neutron capture and returns to lead-206 following beta and alpha decays. Therefore, elements heavier than bismuth-209 cannot be created via the S process. Still, heavier elements such as uranium and radium do exist.
The question of where and how elements heavier than bismuth-209 formed remained unresolved for quite some time. A key to solving this question is the fact that unstable nuclei have short lifetimes. Because of their instability, explosive processes lasting for very short times are needed to create these elements. After many years of study, it was finally concluded that the answer was an immense catastrophic explosion. One possibility is a supernova.
Supernova explosions occur as the result of a rapid drop in the two pressures supporting a star against gravitational contraction. In the iron core of a massive star, when the temperature rises to more than 5 billion degrees Celsius, high-energy gamma rays collide with the iron and disintegrate it. At that moment, an enormous amount of energy is absorbed instantaneously. As a result, the pressure generated by the thermal motion of electrons drops. This triggers gravitational collapse of the iron core. As the collapse proceeds, the density increases. Electrons are then captured by the protons in nuclei, changing them into neutrons and neutrinos. The nuclei become more and more neutron-rich. Since the number of electrons decreases, the electron degeneracy pressure, which primarily supported the star, drops, accelerating the gravitational collapse. The photodisintegration and the electron captures combine to accelerate the collapse further. When the core reaches the density equal to that of the center of a nucleus, neutrons begin adhering to other neutrons. At this point, the collapse is no longer possible. Substances falling in from outer layers collide with this core of nuclear matter violently and are repelled, a reaction that produces strong shock waves.
This is the phenomenon called implosion. When the density reaches a certain limit, repulsion counteracts the collapse, causing an explosion. Researchers discovered that this explosive phenomenon produces a high neutron density, resulting in element formation via the rapid process or R process.
A huge number of neutrons is rapidly absorbed, thereby greatly increasing the mass. The rapid increase in neutron number results in the formation of uranium and radium in about 1 second. This is the R process. Here, neutron captures occur much more rapidly than beta decays. Following the R process, the unstable nuclei containing large numbers of neutrons undergo successive beta decays and give rise to atomic nuclei with larger atomic numbers. Uranium-238, the heaviest naturally formed atomic nucleus, is produced this way. Elements were born with the creation of the universe and reached their present compositions through various processes of nucleosynthesis over the succeeding millennia. But only recently, we have developed the capability to verify the birth and compositional evolution of the elements through astronomical observation and laboratory experiments. So then, what is the key to solving the great puzzles of the R process?
The main key is reactions involving unstable nuclei. The elements of our planet are made of stable nuclei, and thus remain unchanged. However, it is true that the stable nuclei that now exist could not have been created without reactions involving unstable nuclei. So it becomes essential to study interactions with unstable nuclei for understanding the composition of the elements. Such studies become feasible using radioactive ion beams, that is, beams of unstable nuclei.
Unstable nuclei are produced artificially by colliding high-speed heavy ions with a target nucleus. It is expected that studying new unstable nuclei this way will enable us to test the means by which the R process led to the formation of uranium and many other elements in the universe.
We believe that various elements, including uranium, are synthesized through natural processes spanning immense time, say 10 billion years. I think nature presented uranium and radium to tell us about both the origin and the evolution of the universe and the nuclei in it. I therefore believe verifying the course of these elements' birth is a way of returning nature's kindness.
Stardust. All we know was born of it. Then, from where did the elements of stardust come? Extending the limits of scientific knowledge, we are now pursuing the solution of this question.
So what I am doing is basically trying to understand the history of how we got what we have on the Earth. I have a gold ring. This is my wedding band. I want to know how we got gold on the Earth.
You start from the Big Bang, from the very early start. You go through galaxies, through individual stars. You understand stellar objects like novae, supernovae, X-ray bursts, planetary nebula, whatever you name. But then, due to the ejecta, you have an effect on the evolution of the whole galaxy, and so you can later on understand the whole evolution of galaxies.
We are the product of nuclear burning in stars. We're in the process of trying to unravel the puzzle of how all of this came about. And I think that nuclear physics tells us a great deal about the origin of the universe, the origin of the explosions which made the elements.
There are, of course, very fascinating and very exciting developments going on at the moment worldwide, in which we build laboratories, in which these short-lived nuclei are artificially made and give nuclear experimentalists and theorists then later the chance to actually learn about them.
The universe, our place of birth. The very truths governing its boundless reaches must have their origin in the rules governing subatomic particles. Continuity commonly illustrated by the ancient symbol of a snake swallowing its own tail. Liberating the imagination, humankind is drawing closer to elucidating the mystery of element genesis.